Hey, all you cool cats and kittens. I just watched Tiger King, and it's pretty sad. Felt bad for those tigers. Crazy people. Anyways, here's some sample diploma questions from Monday's lesson on EMR and light. So pause the video, try them out yourself, and see how it goes, and I will go through it. Okay, so here is our first one. It's showing EMR and it's showing polarization. So we're trying to rank these from the strongest signal to the weakest signal. So by strongest signal to weakest signal means like how I was showing you with the polarization is the most light going through to the least light going through. So the one that's going to block out all the light is when they're 90 degrees towards each other. So this is the first plane, it's straight up and down, and this one is side to side, which means that all of the light is going to get blocked out. So this is going to be our weakest signal, right? Our strongest signal is when they're the same, because then it lets half the light through. So this is going to be our strongest. And then this one isn't quite 90 degrees, right? When they're the same, then it's the strongest, and then you rotate it 90 degrees and you get the weakest. And then if you rotate it another 90 degrees, and it would be back where it started, it'd be strongest. So this is somewhere in between. So this is the middle here. Okay, so strongest to weakest would be 1, 3, 2. So B is the correct answer. Okay, and number 24, electromagnetic radiation in the synchrotron is generated by these large accelerators. So it's asking how electromagnetic radiation is created. So to create electromagnetic radiation, you need to accelerate charged particles. So one way to accelerate charged particles is to accelerate them, take an electron, move it from the negative to the positive side, and that will create EMR. So EMR will come off. But remember that when you're moving in a circle, right, it says that it accelerates the protons, there's magnetic fields, so there's the FM going in path. So this is from our last unit, FC equals FM. Whenever you're moving in a circle, you're accelerating. The protons, when they move in a circular path by the accelerator, they are accelerating, and any accelerating charged particle will create EMR. Number 22. Which of the following sentences describe the electric and magnetic field components? So they're always going to be perpendicular to each other. Everything's perpendicular to each other. So if the wave is moving this way and the electric field is going this way, then the magnetic field is going into the page and out of the page like that. They're all at 90 degrees angles to each other. Okay, and this one, so give it a go. It's just a lot of reading. You can see its answers the next 3 questions, so I'm just asking one. So all you need to know for this one is this. So it asks the region of the EMR spectrum in which ground penetrating radar is classified. So ground penetrating radar can be used to examine the subsurface structures and search for evidence of specific rock formations that would indicate previous presence of water. So the device has an antenna of 1 meter, which is half the wavelength of the radar's EMR, so that ground penetrating radar. So it looks like the ground penetrating radar is 2 meters. And if you're big, like within the meters, like anywhere from 1 kilometer to 1 meter, that's all in the radio range. Okay. All these guys are really, really small. So the only big one is radio. So the bigger the waves, they're in radio. Okay, so today we're going to talk about calculating the speed of light. How do you do that? So we're going to explain qualitatively various methods of measuring the speed of EMR. And then you need to know a Michelson type experiment. This is the most important one from here. So we'll start off with a video of a little bit of review from our last lesson, and we'll watch that, and then we will continue on.
Light has long been a fascination of scientists, but it travels so fast that it was very difficult to study. Isaac Newton, the brilliant English physicist who lived in the 17th century, believed that light was made up of extremely small particles, but he could not explain how it traveled. Others believed that light was energy that traveled in waves, but they could not figure out how light waves could travel through space. By that time, quite a lot was known about sound, and it was felt that all energy needed a medium in which to travel. Scientists concluded that space had to be filled with some type of matter they called ether, which acted as the medium for light. In 1873, James Clerk Maxwell, a British physicist, resolved most of these problems. Maxwell developed equations based on the earlier work of Michael Faraday, who had demonstrated the link between electric fields and magnetic fields. The oscillations, or movements back and forth of electric charges, generate electromagnetic waves of energy, which propagate as transverse waves. Maxwell's calculations of the velocity of these waves match the speed of light, and led him to predict that light is an electromagnetic wave. Since electric and magnetic fields can exist in both a material substance and a vacuum, these waves do not require a medium and can travel through air, water, or the vacuum of space. Once that was understood, physicists abandoned the notion of ether. If we could see them, transverse waves would look something like the waves in this rope, or the ripples on the surface of a pond. This animation of an electromagnetic wave shows both the electrical and magnetic component of the wave. Note the two parts of the waves are at right angles to each other. Maxwell believed that electromagnetic waves were only energy, but it is now known that they are both waves of energy and particles called photons. This is called the wave-particle duality. All electromagnetic waves travel through space at the speed of light. Our greatest source of electromagnetic waves is the sun. But it is also the energy in radio and television waves, electric lights, the light emitted from fire, the atoms that make up matter, and much more. Electromagnetic waves are everywhere in our universe.
Okay, so I got a couple questions actually just one question for you. How would you try and measure the speed of light? Think about that for a second. If you wanted to measure the speed of light, what would you do? So, most people, they tell me, I don't know, if you had a guy and you shine a flashlight, that's a flashlight, shine a flashlight at someone, and then have another person here sort of tell when you shine that flashlight and be like, yes, I raised my hand. This is this long hand now. Yes, that's when I see the flashlight and try to measure the time difference in between. So that's the most common way that I get. So knowing that light could travel at that speed, how many seconds would it take light to travel from Vancouver to Toronto, which is that many kilometers away? Okay, so all we need to do is use V equals D over T, and T equals D over V. So we have 4,412 kilometers. If I want to switch that into meters, just add 3 zeros. So that's the difference from Toronto to Vancouver. And then 3 times 10 to the 8 meters per second is my speed. So if we try to type that in, oops, there we go. So 4,412, 123, divided by 3 times 10 to the 8. Light could travel from Vancouver to Toronto in 0.014 seconds. So if you have your phone handy, open your stopwatch and try to start and stop your stopwatch in that time. I'm guessing that not very many of you will be able to do it, and it's such a tiny time, and that's Vancouver to Toronto, so to light would look like it was instantaneous if you were a smaller area, right? So Galileo had a similar idea to this. So Galileo was the first one to try to measure the speed of light. So Galileo and his assistant would stand on adjacent hills about 1 kilometer away. What Galileo would do is he would uncover his lantern. When his assistant saw the uncovered lantern, he would uncover his, and then Galileo would use his pulse, because they didn't have stopwatches, to try to measure the difference in time. So it can go from Toronto to Vancouver in 0.014 seconds, and they're 1 kilometer away, and he's trying to use his pulse. I don't think you can get a fraction of a pulse, so it didn't work out very well. That's how long it takes light to travel there and back, 2 kilometers. So Galileo soon learned his pulse was not an appropriate time measure, and he was unable to get a calculation for the speed of light, so it was unknown. So here's a couple of gifts that I have. So this is, if you're trying to measure the speed of light on Earth, this is how fast the speed of light is. It can go 7.5 orbits per second at the surface. So it orbits the Earth 7.5 times every second, which is crazy fast. It looks insanely fast. But if you start increasing your distance, the speed of light slows down. So if you're sending light from the Earth to the moon, well, now we can see that light a little bit better. So surface to surface in 1.255 seconds. So from the Earth to the moon takes 1.255 seconds because our distance is bigger. So if we create an even bigger distance, then we can slow down the speed of light even more. So now we want to go from the Earth to Mars. And this little beam here, that's the speed of light. That's how fast it's going. So when you make your distance really big, well, the speed of light doesn't seem that fast anymore. It can get to Mars in 3 minutes and 2 seconds, but that still seems a lot slower than when we were trying to measure it on the surface of the Earth with this guy here. No, it doesn't want to work anymore. There it goes. Yeah, so much, much slower than that original one. So, yeah. So that's what scientists did. They're like, well, let's get a bigger space. So they did even bigger space than this, and they used, so Romer and Huygens was the guy who thought that light was a wave. Olaus Romer and Christian Huygens, they used Jupiter's moon to calculate the speed of light. So they went even further than Mars, and they went to Jupiter. So Jupiter's moon, Io's period of revolution has been accurately measured from years of astronomical data, and Romer knew that Io should be eclipsed and disappear behind Jupiter every 42.5 hours. Okay, so they know that. But what he found was that it eclipsed later when Earth was further from Jupiter and eclipsed sooner when Earth was closer. So the time difference was 22 minutes. So Huygens reasoned that the difference in time was due to the time it took light to travel from Jupiter to Earth. So here's Io over here, here's Earth, so here it's eclipsing behind. So this is the distance that it takes light from Io to reach Earth when it's closest. And this is the distance it takes light to travel when Earth is further, right? So he found that the distance was the time was 22 minutes. It was 22 minutes different, and that's because it took the light 22 extra minutes to travel there. And they also knew that Earth's orbital diameter was about 3 times 10 to the 11 meters. So they knew a distance, they knew a time. Well, that's really easy to calculate. We can just use V equals D over T. So the distance was 3 times 10 to the 11 meters. And then the time was 22 minutes. So minutes down here, seconds up here, 60 seconds in 1 minute. Those will cancel out. So if we want to calculate that, we just have to go 3 times 10 to the 11 was the distance, divided by 22 times 60. And we end up getting that, right? Which is pretty close. If we subtract 3 times 10 to the 8, which is our answer, and then divide by 3 times 10 to the 8, just ignore the negative on there, times 100%. So we have about 24% error. Just ignore the negative. There's absolute symbols with that. So we have about 25% error, which seems bad, but we also went from Galileo saying no idea to within pretty close. Like that's 10 to the 8 is it's pretty solid. So they did a good job, and they did that by making the distance really big. So now light was slowed down for them. Okay, it's the next guy to do it. He was able to do it on Earth. And if you're doing it on Earth, you can do it. You just need a really, really accurate measuring device. So Armand Fizeau became the first person to measure the speed of light on Earth. He allowed light to pass through a toothed wheel and reflect it off a mirror 8.63 kilometers away. So he's increasing his distance, right? So the toothed wheel would rotate, so the original image was allowed to pass through, but the reflected image would be blocked by the tooth. So that's what he was looking to do. So here's his light source. So you think of light as like a light bullet. So here's his light source. So we take this light bullet, it would bounce off the mirror, and then it would go through one of the openings in the tooth here. So it'd go through that opening. It would go 8.63 kilometers, bounce off this mirror, go 8.63 kilometers back. And if this toothed wheel was spinning at the exact right speed, at the exact right frequency, when that beam of light came back, it would try to go through the same opening, but that toothed wheel would have rotated just a little bit, so it'd be blocked out, so we'd see no image here. That's what he was looking to do. He was looking to block it out perfectly so there's no image. So we used the rotational frequency of the wheel to determine the time it took the light to travel there and back. Okay. So he found that the speed of light was this, which is a little bit closer and a little bit better. So here's a calculation. A disk with 600 cogs must spin at 1100 hertz for the light to travel a distance of 1164 meters, reflect off a mirror in 1164 back and be blocked by the adjacent cog. The beam of light takes this time to do the trip. Calculate the speed of light. So again, this is just a V equals D over T. All of these are just V equals D over T. So it's got to go the 1164 meters, and then it's got to always come back in its experiment. So my distance is going to be 2 times 1164 meters. And they give us the time here, 7.5075 times 10 to the negative 6 seconds. Right, and we plug that into our calculator up here. Let's lift that up a little bit. So we would go 2 times 1164 divided by 7.5075 times 10 to the negative 6. And they should all be pretty close, right? Pretty close to the speed of light. So that's what we get. That's a little bit better. Okay, so this is the experiment that you really need to know about. It's the most commonly tested one. It's very similar, but instead of using a toothed wheel, Michelson used an 8-sided mirror. Used a very intense light source. It was directed at an 8-sided mirror. There's also questions with 12-sided, but they all work the same way, and would reflect the light to a curved mirror 35 kilometers away. So it's actually crazy how far he was able to get that light to travel. So if the wheel makes a 1/8 of rotation, the light should be able to be seen from the telescope. When the mirror rotated at 533 hertz, he was able to see light from his telescope. So I'll show you a picture here. So this is a light source. So think of a light as like a bullet again. So here's a little light bullet. It goes, hits off mirror 1, go 35 meters, could be kilometers, go 35 kilometers back. So this is our light. So in that time, he wants that mirror to rotate 1/8 of rotation, right? So now that the light beam is over here, everything's moved up one. So this is going to be 1, this is going to be 2, this is going to be 3, this is going to be 4. So everything is rotated 1/8 of rotation. And if that frequency is perfect, then it's going to bounce to the telescope and he's going to be able to see light. If this is spinning too fast, what's going to happen is the side is going to be a little bit too far over and it's going to glance off like that. If it's a little bit too slow, this side will be over here and then the light beam will reflect that way. But if it's going the exact right speed where it can do 1/8 of rotation, then he'll be able to see the light from the telescope. Okay, so let's do this question. I'm going to switch. This one's a little bit more in depth, so I'm going to switch to this. So for all of these, we need to use V equals d over t. Right, we're trying to find the speed of light, and we know our distance, right? It's got to go 35 kilometers, or that many meters, and it's got to go there, and it's got to go back, right? So it's got to go 35,000 meters there, and 35,000 meters back. Okay. For our time, we need to do a little bit of more work with that. So the question originally said that the last one said that he had to spin at 533 hertz. So 533 hertz is the same thing as I'm not writing on the, you can't see my screen anymore. So 533 hertz is the same thing as 533 rotations per every 1 second. So this is a frequency, that's not what we want for a time. We want our answer in seconds. So what we should do is we should 1 over that. So we take our 533 and we 1 over it. And what we end up getting is we get, so this is how many seconds, and when we inverse it, turn into a period, that's how long it takes to do 1 rotation. But remember, we don't want to do 1 rotation. For the time it takes for the light to travel there and back, we only want this light to do 1/8 of rotation, right? 1 will be where 2 is, 2 will be where 3 is, like that. So it's not a full rotation, it's only 1/8 of a rotation. So we only want 1/8 of that answer because that we want the time it takes to do 1/8 of a rotation. So for that, I get 2.3452156. So 3,500. So I'm ready to get my answer. 35,000 times 2 divided by my answer from before, and I get my answer to be 2.98 times 10 to the 8 meters per second, which is pretty dang close to our answer that we have here, and that's really good. Right, so this is the part that people struggle with, right? We use the frequency, find the period that's for 1 rotation, but we only want 1/8 of a rotation. Okay, so we're gonna do another example here. This is slightly different. So there's just a couple ways of doing this question. So the first way I showed you is one, and this is another way. An 8-sided mirror is used to measure the speed of light. What frequency would the mirror need to rotate at to have the light pulse be detected if the mirror is 41 kilometers away? Okay. So we have our 8-sided mirror. Oops, I almost drew it perfectly, but screwed up there. So the light has got to bounce off this side, and in this question, 41 kilometers away, then it's going to bounce back, and when it bounces back, it does 1/8 of rotation. So just 1/8 of rotation, 41 kilometers back. And we're looking for the frequency, so we can use V equals d over t to answer that. And if we want to find frequency, we need time. Right, so our distance is 82,000, because it's got to go 82 kilometers, switch into meters, so 82,000 meters. And our speed, we can use the speed of light. Some questions do that. We're not trying to calculate that, so we can do that. So 82,000 divided by 3 times 10 to the 8. So I get an answer of 2.73 repeated times 10 to the negative 4 seconds. So at this point, you need to stop and think, what is happening in that time, right? Well, it's rotating, that's for 1/8 of a rotation, right? But if I want to know the frequency, I need, right? If I want to find the frequency, I need for one full rotation. So this is 1/8 of rotation. Then we multiply that by 8. We get 0.002186 repeated seconds, and that's for one rotation. And that's the thing that students have the most trouble with, is they don't know when to multiply by 8, divide by 8. You gotta think, right, what's happening in that time. Yeah. So that's for a full rotation, and then we just went over it, because now this is a period, so our frequency is gonna be 457 hertz. Hopefully that goes okay. Okay, yeah, so that's pretty much it. There's some extra stuff in the notes, but that's just fun stuff. So, oops, gotta switch my screen. So this is your homework. So this is Romer and Huygens stuff, 1, 2, 3, 4, and this is Michelson stuff, 10, 11, 12, 13, 14. So give it a go, see how it goes, and let me know if you have any trouble, and I can Google Meet you, I can email you, I can make you videos. Yeah, that's pretty much it. So enjoy the lesson.